Thank you. Yeah, good afternoon, everybody. As you can see, this presentation is around the use of UV-Vis for biomolecule measurements. I'm sure you all know that UV-Vis is one of the most widespread techniques for measurement of biomolecules because all biomolecules will absorb somewhere within the UV-Vis spectral range. It's a very versatile technique because you can use UV-Vis for qualitative analysis, for quantitation. You can use it to follow reactions as a function of time or temperature. You can also use it to study how your biomolecule behaves in different environments. It's also a very affordable technique. When you compare UV-Vis to techniques like NMR and LC-MS, UV-Vis is small change. So in my opinion, it's a technique that every lab should have a UV-Vis. And if your lab doesn't have one, I suspect it does, but if it doesn't, then hopefully this presentation might inspire you to go and buy one or give you some ideas for how it could benefit your research. Now at Agilent, we're very proud that our portfolio of UV-Vis instruments carries the Carey brand name. So Carey is named after this guy, Howard Carey. So he was an American inventor, and he's credited as being the person who developed the first commercial UV-Vis spectrophotometers. So the first single beam instruments and the first double beam instruments as well. And Carey was a real free-thinking guy. He liked to look at a problem and solve it himself and not be influenced by what other people had done before him. So his designs were very revolutionary, very far ahead of their time. And in our R&D center in Melbourne, as you walk into the reception, there's a kind of a museum area dedicated to Carey. We have some examples of his early instruments. What's really remarkable is that hanging on the walls, we have framed copies of the blueprints of some of his early designs. And if you look at the blueprints, what you'll see is that actually, over the last more than 75 years, nothing has really changed in UV-Vis. Okay, the lamps are still in the same place, the detector's still there. Almost every single spectrometer on the market still follows the original design from Howard Carey. So a few years ago, Agilent were looking to retire the Carey 100 and 300 series of instruments. They've been in service for more than 20 years. So we gave the design team the brief to replace them, and we encouraged them to be creative in the spirit of Carey. And what they came up with was the Carey 3500. And this is it's an unusual design of instrument. It's unusual, first of all, because it's an instrument that's in two pieces. So the first piece is what we refer to as the engine. So inside the engine, you have a pair of monochromators which work in tandem with each other. So the first monochromator selects the wavelength of light you want to use, and the second monochromator cleans that light up. So it gets rid of the stray light, and that gives us increased absorbance range and better sensitivity. There are also variable slits in there, so you can control the spectral bandwidth and you can optimize the resolution of your spectrum. But principally, instead of using the traditional deuterium and halogen lamp combination as the light source, inside the engine, we now use a xenon pulsed lamp source, a xenon flash lamp. And these xenon flash lamps, they have a number of benefits. They're very, very bright light sources, so you're able to get a lot more light to the sample. But because the light is delivered in small pulses, you don't photo-degrade the sample. So it's great for biomolecule research because you don't photo-bleach or damage your samples in any way. But also the xenon lamps, they last pretty much forever. So with the Carey 3500, the lamp is actually covered under warranty for 10 years. So we don't expect you to ever have to replace it. So the engine can be mated together with different sampling modules. So you simply put the two together, and then there's a handle on the side. You turn that through 180 degrees, and it locks the two pieces together. So when we launched the instrument, we created a range of sampling modules based around simple liquid measurements in cuvettes. So we have what we call the compact and multi-cell modules. So the compact modules simply have two cuvette positions for sample and reference, and the multi-cell, these modules have 8 sample positions. But again, what's unusual, what's novel about the multi-cell is that each of the 8 positions has its own detector. So all 8 sample positions are measured simultaneously. You can also get these modules either with or without temperature control. Obviously, for biomeasurements, temperature control is very, very important. So during the kind of R&D phase, our engineers went and interviewed our existing users. So the existing users, they had a setup that looked like this. So they carry 100 or 300 spectrometer with a Peltier thermostated cell changer, so an electrically heated cell changer. With these type of Peltier devices, you need like a cooling circuit to take away the excess heat. So these Peltier cell changers were connected to this thing, a big water chiller. So there was water recirculating during the experiment. And so when we asked people what they didn't like about this, they said, well, obviously with the water, we've had leaks. The other things which they've had a lot of the time, if they haven't put enough glycol in the water system, and so then you get bacterial growth and it kind of gums everything up. So we listened to their concerns, and the R&D team came up with a really neat and elegant solution in the form of a completely air-cooled unit. So there's no water recirculation, no possibility of leaks or bacterial growth. You have the same great temperature range, fantastic temperature accuracy, and within the cuvette positions, there's the possibility to do magnetic stirring. But then the engineers, they really took it to the next level, and they introduced this concept of kind of zonal heating or multi-zone heating. So with the 8-position system, you can have all 8 positions operating at the same temperature, or you can split them in the middle and have 4 cells, or a reference and 3 samples operating at one temperature, and then a reference and 3 at a different temperature. Or you can go all out and have it split into 4 pieces and have sample and reference at 4 completely independent temperatures, all being measured simultaneously. So it gives you the possibility to really multiplex your experiments and to get through a lot of the method optimization stage a lot faster. So now you've seen what the Curie 3500 looks like. Let's look at some of the things that it can do. So one of the most common applications for UV-Vis is for simple purity determination of DNA and RNA. So DNA and RNA absorb at 260 nanometer. They don't absorb at 280. So we use a simple ratio of 260 to 280 nanometer. And the conventional wisdom is that for pure DNA, you should get a value around 1.8. But actually, that value can be influenced by the matrix. And so things like buffer concentration, as the buffer concentration is increased and the conditions become more alkaline, you can see that ratio goes from 1.8 up to around 2.1. So the application isn't as straightforward as you might imagine. We've actually published a white paper on this recently where we talk all about method optimization and things that you can do to influence this number. Another very common application is protein quantitation. Often the protein samples are in very low quantity, so it requires the use of a low volume cuvette, so the type of cuvette like this with the blacked out sides and the sort of small window. With the Curie 3500, the beam on the Curie 3500 is very collimated, and it only measures about 1.5 by 1.5 millimeters. So even with that very small window, we're able to get all of our light energy through the sample. We're not wasting any light on the cuvette. So with these type of measurements, we construct a calibration curve using standards with known concentrations of protein, typically a kind of readily available protein like BSA or lysozyme, and then we use that calibration to measure our unknowns. And it works really well if you have a pure protein. If your proteins are less pure, then you can use other approaches like colorimetric approaches, which obviously then the measurement takes place in the visible range. You can also look at protein aggregation. You can do that by looking at the ratio between 280 nanometers and 350 nanometers. So at 350, proteins don't absorb, but you see an increase at 350 if your proteins are aggregating. So within the Curie 3500 software, you can program it to measure what we call a aggregation index, which is this 350-280 ratio. And then you can look to see, you know, how the proteins are aggregating, in this case, you know, as a function of time. I said you can also look at how your biomolecule behaves in different environments. So look at the effect of pH, buffer concentration, and so on. Again, this is a good example, looking at these amino acids in protein or a monoclonal antibody. You take a scan and then you apply a second derivative to that scan. What you end up with is two peaks, which I've labeled here as A and B. And by looking at the ratio between those two peaks, you can look to see how kind of exposed those amino acids are. So in a way, it's a measure of the kind of the shape of the protein and how it changes in its environment. And this is an example of the use of the multi-zone capability. So you can imagine this being applied to something like an enzyme assay. So you can have your enzyme, you know, in solution at 4 completely independent temperatures. You can add the substrate in and follow that reaction. And you can either do that at fixed wavelength, or as you can see in this example here, you can do it by collecting complete scans as a function of time. And then at the end of the experiment, you can take a slice through the data at any particular wavelength, and you can extract the rate curve at that specific wavelength. But where the Curie 3500 really excels is for thermal denaturation experiments, in particular DNA melting. So I'm sure most of you already done this type of experiment. So you take double-stranded DNA and you heat it up to high temperature, and typically somewhere between 75 and 85 degrees C. And those double strands start to dissociate into single-stranded DNA, and you get a big rise in the overall absorbance. And this technique is very sensitive to changes in the base pair sequence. And generally speaking, as the GC content increases, the melt temperature increases. Now, historically, these type of experiments had to be run relatively slowly in order to collect enough data points across this transition to give you an accurate determination of the melt temperature. But now with the Curie 3500, we have such excellent close control over the temperature that we can actually run these experiments really, really quickly. We can take an experiment that used to take hours and we can compress it down into a matter of minutes. One of the reasons for that is because the R&D team also developed a new type of temperature probe. So these are bioinert polymer thermocouples, so very thin, very flexible thermocouples that simply slot into the cuvette. So they slot down the side so they don't interfere with the light beam, and they give a very accurate, direct reading of the actual sample temperature. On the other end of the probe is what looks like a USB connection, and that USB connection can be plugged into any one of the sample positions. So here you can see we took an experiment where we used ramp rates starting from 0.5 degree C per minute all the way up to 30 degrees C per minute. And when you apply a first derivative in order to calculate the melt temperature, you get exactly the same melt value, plus minus about 0.2 degrees C. Okay, so so you're able to run a lot faster, but without sacrificing any accuracy. So there you have it. I say hopefully that's given you some ideas for things if you weren't already using them anyway. Please do come and have a chat with me during the coffee break. But in the meantime, if anybody's got any questions, I'll be more than happy to answer them. Thank you.